Okay, I got everybody who's at least in my main screen here. Okay, so today's topics are water and light. I hope that you've all had a chance to read chapter 3, really in its entirety. It's a short chapter, and almost everything I think will be review for you from probably general chemistry. But water is really, you know, the stuff of life, and it is what makes a lake different from anything else on, you know, from the land, is that it's water. So anyways, that's all very important. And the reading questions really help you, hopefully, to focus on what exactly you need to know. And then chapter 10 is longer and has a bunch of stuff that you don't need to know. And I think the reading questions kind of point you at the specific points that you need to focus on. I don't think there's anything in chapter 10 that's going to hurt you if you read pages that are not required. You know, it's good for you, it's good information, but you know, it's hard to know everything, and I think the reading questions will help you focus on the specific things that you really need to know. All right, so what we're talking about today is water and light. We're going to do it in that order. We're going to start with water. I'm assuming that this was a review for you, that you learned it before, that you read it again in Calf, and you wrote down some notes for yourself. And for many of you, you probably already have some ideas about why the properties of water are important. I would bet, well, I don't really bet, I'm not a gambling person, but you know, I'm pretty sure that at least some of you have some misconceptions about the properties of water that are important and why they're important in the environment. And I say this with some confidence because I have heard scientists who are not limnologists, but scientists, say some of these things that actually are incorrect. So, you know, you're totally to be forgiven if you've come into this class with some wrong ideas. And now what we're going to do is try to surface those ideas and correct them. Yeah. So let me tell you how we're going to do this. I got a PowerPoint here. See if we can all see it. Hey, Jeffrey, can you see that? Yeah, Jeffrey can see that. Okay, so they say, like I read this somewhere, that one of the best ways to help people, students in particular, correct their misconceptions is to first have them talk with other students in a kind of like low-key, non-threatening way. And then when in talking, they discover some kind of disagreement, this should open their mind to the possibility that they might be wrong. Okay, now we know people who, you know, when they disagree with somebody, pretty much 100% of the time, completely confident that the other person is wrong. Okay, and we know that those people are really annoying, and we know that those people themselves are often wrong, because that kind of like permanent confidence is really a handicap, and it's a serious handicap for scientist. And I'm assuming that's not your problem. I don't think anybody here has that problem. Anyways, I'm going to put you in groups. I'm going to ask you to answer some questions, and I would like you to pay attention to if there's anything that you're uncertain about or if people in your group disagree on. Okay, so we're going to talk about water, and before we get started on the lecture about water, we're going to start with some questions, which are, page up, there we go. All right, here are the questions that I want you to address. Why does ice float? Because you've all observed ice floating, right? Right. Why does ice float? Second of all, why is it cooler by a lake in the summertime? People go to the lake because it's cooler, even just sitting on the shore. Why is that? 3, I think you know by now that lakes stratify in the summer. Why do they do that? Why do lakes stratify into an epilimnion and a hypolimnion? And then, well, the big question, looking at all the different properties of water, which properties of water are most important for life in lakes? Because you got like density and specific heat and heat of fusion and heat of vaporization and viscosity. So, right, water has a lot of different properties. Which of those properties are most important for our purposes, understanding life, what it's like to be life in lakes? All right, so these are the 4 questions, and I might just like save this somewhere, but anyways, hopefully you're writing these questions down. I'll give you a minute to do that, and then I'm gonna give you 10 minutes to try to answer these questions, or at least the first 3. Okay. So I'll give you a minute to write these questions down. Are there any questions any questions about this assignment? And we're just going to have some random Zoom rooms with, 3 or 4 people in each of them. 3, 4, wait, 3. Some random groups with 3 or 4 people in each of them. Come on, Zoom. Okay, here we go. I'm going to open it, and you'll have about 10 minutes to try to answer these questions. Okay.
Hello.
Hello.
How's everyone doing today?
Yeah.
All right. Does anyone want to do a whiteboard? Or can anyone do a whiteboard?
I can. I just don't know. I haven't ever tried it before, so I don't know if I'll be able to re-pull up the whiteboard in the end. Do you know what I mean? Like when you download it.
Yeah.
But I could also screen share. I just have the questions on my screen, and we could just do notes off that. Do you want to do that?
Yeah, that'll work.
Okay.
So first question, why does ice float? Well, it's less dense than liquid water. I don't remember the specifics I just know that when ice solidifies, something about the spacing in their molecules make it less dense.
Yeah, so since like the water is heavier, it places like the lighter ice on top. I don't know.
Sorry, could you say that one more time?
Well, basically like since the like water is heavier,
Mhm.
it displaces the lighter ice on top.
Yeah. Yeah, I would agree with that. For the next one, why is it cooler by a lake in the summertime? Does anyone have any ideas for that one?
Um, I think it has something to do with like the heat capacity of water.
Mm.
Like I'm trying to remember specifically where it like retains heat
Yeah,
better.
yeah.
And
So one thing that I've heard is that um, for water, it takes longer for it to change temperature than land. Is that true?
that sounds right.
Because like if, for example, if you're closer to the ocean, your your weather is going to be more predictable, or it's going to be more of like the same kind of a temperature. You're going to have less of a temperature change versus if you're more inland, like your temperatures will go way higher or way lower because you're not as close to water. So water's normally at like 32 degrees so that it can stay as water, but it'll stay between like 32, maybe 70 degrees, but it doesn't like get too cold and it doesn't get too hot. I've heard that. Do you guys want to move on to the next one, or does anyone else have any
Yeah,
ideas? Okay.
yeah, I think that's good enough for, and like I said, she'll go through specifics for us.
Right. For the stratification of lakes in the summertime, doesn't that one have to do more with energy? So like if there's freezing on top, if the water's freezing on top, then there's not as much wind that can get through. Because she talked about this one, and it was more like wind involved. But if a lake doesn't have any wind happening, then it will separate into different parts.
Does it have anything to do with sunlight as well?
Yeah.
Yeah, and I think if I remember from what we read in like the first unit, like the um the lower level becomes less like the density of the water, all the stratification levels kind of like based on density, like
Hmm.
equalize. So then when wind's able to come through, it's able to mix and cause like that turnover. Or am I thinking of no, I'm thinking or am I thinking of spring?
Well, yeah, it was spring and fall where the wind does the
Yeah,
turnover,
that's yeah, you're right.
and that's like a dim dim dialectic, something like that. Yeah, a dialectic lake. So, but I mean, if water is more hot, it'll rise, and if it's colder, it'll lower. But then she'll probably ask the question of why why is ice on top, and that's because ice is less dense. So yeah, I don't know. Like when you're boiling a pot of water, the water will move throughout because the hot air rises, the hot water will rise. That's what I've heard at least. So I don't know.
Yeah, I just did a quick little Google search just to see if like what we were saying. Yeah, it just says like throughout the summer, wind and waves cause the warming water of the epilimnion to mix deeper and deeper, slowly incorporating hypolimnetic water throughout the metalimnion.
Yeah. Yeah. Yep. All right. Next question, which is the big one. Which properties of water are most important to life in lakes and why?
So kind of going back to that first one, I know for like aquatic systems, like the lower density is important because then it doesn't freeze all the way through, so organisms can still like survive underneath the ice layers.
Mhm.
From what I remember from biology, not knowing the specifics, but just generally, I know the polarity of water is one of those like key unique features of it.
Yeah.
And then from what I'm remembering too, without knowing the specifics, I know the cohesion of water.
Mhm. Like with different life forms that will bounce around on top of the lake.
I'm trying to remember specifically. I wish I had my old notebook and we talked about it. Um, we can maybe skip that one. I could just be spitballing. I just swore I remember talking about like the cohesion of water.
Yeah.
And I think another one would be like water's kind of like, this could be like a stretch here, but water is kind of looked at as like the universal solvent. So on like a chemical level, a lot of things can dissolve in water.
Yeah. Yeah. Like salt and all that.
And then maybe we could reference to that like high specific heat, how it's able to retain, because like from friends of mine who have like relatives who live up on Lake Superior, they always talk about, how it's cooler near the lake and how like it had like its own little microclimate and stuff like that for big water, big bodies of lakes and stuff like that.
Right, right. Yeah.
Yeah, I think that's good.
Okay. Sounds
Cool.
good.
All right, welcome back. Hope you had a productive conversation. Um, let's go through some slides. All right, so let me see if I can arrange my desktop here. All right, so why does ice float? Anybody want to tell me why they think ice floats? I did away with the breakout groups, so I can't call you by groups, but for some reason, Bree is at the top of my list here. Hey, Bree, do you know why ice floats?
Hold on. Isn't it like less dense?
Yes, it's less dense than liquid water, right? Great. Hey, Keenan, is next here on my list. Do you know why is it cooler by a lake in the summertime?
I feel like you're picking on our group.
I don't know. It's just the order Zoom has you in on my face list. I could pick up somebody else.
No, it's fine. So I had to look up kind of what the lake effect is.
Oh, okay. Well, you got the wrong answer then.
Oh,
Let's-
okay.
yeah.
Okay.
So let's. How about Sam Thomas? I don't think you were on that same group. Why do you think it's cool? Why do you think it's cooler by a lake in the summertime?
I said it had to do with like the specific heat, so water takes more energy to heat up, so it stays cooler longer.
Yeah, that's actually not correct.
Oh,
That's the answer you're going to get if you look it up.
yeah, that's what I did.
And that's probably what, if anybody ever taught you about this, that's probably what they taught you. And yet it is wrong, amazingly. And I'll tell you why. I'll tell you how you know it's wrong. Because that effect goes away in the winter. And yet the water is still there, right? If it was all about the specific heat of water, then you would see the same effect in the summer as in the winter. But you don't. In the wintertime, it's really the same temperature near a lake as it is far away from a lake. And yet that answer about specific heat is so attractive. You know, it seems logical, and so logical, in fact, that you ignore your common sense experience. Yeah. But I will tell you what the right answer is. I could tell you right now. Okay, I'll tell you right now. The answer is because water moves, right? So the water at the surface absorbs heat and warms up. And then because water moves, that heat gets distributed down deeper into the lake, taking it away from the surface. The ground heats up also, but it doesn't move. And so the sunlight heats the surface of the lake and the land equally, but the heat that is absorbed by the surface of the lake mixes down into the lake and is distributed throughout this large body of water. Whereas the heat that warms up, the sunlight that heats up the surface of the soil, that heat just stays there at the surface of the soil. The soil doesn't like move around typically, unless it's like quicksand or something. Yeah. So you get the same amount of heat distributed through a large object, which is to say the lake water, versus that amount of heat distributed through just the surface layer of the soil. So the soil heats up a lot more, rises in temperature, and heats the air above it. The lake doesn't heat up nearly as much. And then that lower temperature heats the air above it, but not as much. So it's really more about the fact that the water moves than the fact that water has a high specific heat. And I think that that is a fact that most people do not know for some reason. Okay. Speaking of lakes moving and things moving and not moving, why do lakes stratify in the summer? I see Saul's smiling face on my little list here. Saul, did you guys come up with an answer? Why do lakes stratify in summer?
Yeah, we talked about density. So the cooler water at the bottom of the lake stays relatively cool compared to the water on the top, making it denser. So it's not likely to mix as much with the warmer water.
Yeah, that's exactly right. Once you've got a situation with cooler water below warmer water, you're going to have a situation with more denser water being below less dense water. And the greater the difference in temperature, the greater the difference in density, the greater the difference in density, the harder it is for the wind to mix those two. So it's just kind of self-perpetuating. And let's go down to the next question. Last question, which properties of water did you think were the most important for life in the lake? I mean, water's a substance, it's got lots of properties. Which of those do you think are the most important? Ooh, okay, I got my room list back here. Let's go to, and Dolly, James, Kat, and Christina, what did you guys, I'm gonna ask each group this, what did you think are the most important properties of water? So, and Dolly, James, Kat, or Christina, room 4.
For us, we talked about how like the density of water is important with lakes. So if you've got ice on top, that really helps fish survive the winter time because they have the water to live. So we talked a bit about that.
Yeah. All right. So yeah, and the curious relationship between temperature and density for water is a bunch of properties or something. How about room 3? Brianna, Hannah, Keenan, what did you guys think were the most important properties of water?
We didn't really discuss it. We stuck mostly to the first 3 questions, but I agree with Kat's group. Actually, I had always thought that the property that water has that allows it to freeze at the top instead of from the bottom up was the most important because, like she said, it allows life to live in the lake even when it's freezing.
Yeah, that's a big thing in Minnesota, isn't it? All right, how about room 2, Sam, Saul, Tiffany, and Jew? Did you have any other properties of water that you thought were important?
We didn't really get to discussing this question either, but based off the reading, I would think that the specific heat is important. Just keeping the temperature from being variable throughout the different seasons should make it easier on the bodies of the aquatic organisms living there.
Yeah, that makes sense. That it prevents the temperature of the water from changing rapidly.
Yeah.
Yeah, whereas something, the opposite would be something like, pavement, tar, which like heats up and cools down and heats up and cools down. So obviously a much lower specific heat than water has. Okay, how about room 1, Abdul Desiree, Jeng, and Sam Thomas? Did you guys have any other properties of water that you felt were important?
No, we pretty much said the same thing that the other groups did.
Stuck the same things.
Yeah,
Okay.
I mean, I also thought that maybe like oxygen content of lakes, like if it's, oligotrophic and eutrophic lakes might support different life.
Something, okay.
Yeah.
All right. All right, well, let me show you some slides and just talk you through some stuff to just, obviously I think you know this already, but I wanna review it and highlight some things. Okay. Okay, so here we got a picture of water. We got obviously solid water on the left. Let's see if I've got my annotate tool here. We got solid water on the left. We got liquid water on the right. We got more liquid water up here in this cartoon of a cloud because when water is vapor, it's invisible. So we got solid, liquid, and gas. And water, when it is a gas, is a colorless, odorless gas. You can't see it. The room that you're in right now has got water in the air and you can't see it. You call it humidity. Now, when it condenses into liquid, water drops, then you can see it. So there's tons of water in the air that you can't see. When it condenses into liquid, it forms a cloud, then you can see it. Now there's a bunch of important properties that we have involved here, right? Let's see if I can draw an arrow, right? To go from here to here, this is going from a liquid to a solid. Did I say that right? A solid to a liquid, or vice versa, from a liquid to a solid. There we go. From solid to liquid or liquid to solid. This takes a lot of heat to make this transition. And this is the heat of, well, it depends on what you want to call it. You might call it the heat of melting if you're going from right to left. You might call it the heat of solidification if you're going from left to right. I'm saying this wrong, from right to left. You know what I mean, the heat of fusion versus the heat of melting. And this is This is a huge amount of heat, right? This is, anybody want to guess? How many times more heat does it take to convert solid water to liquid water, like without changing its temperature? How much heat does it take? Now, you know that the specific heat of water as a liquid is about 1 calorie per gram, right? It takes 1 calorie or 4.187 joules to raise the temperature of 1 gram of liquid water 1 degree Celsius, right? 1. So people say the specific heat is 1, and that means it's 1 calorie to raise 1 gram 1 degree. How much heat does it take to convert 1 gram of 0 degree ice into 1 gram of 0 degree liquid water? How much more? How much less? How much, what's the multiple here? Does anybody happen to know? How much heat does it take? Does it take more heat to convert 1 gram from ice to water? Or does it take more heat to raise 1 gram by 1 degree? Is that not a clear question? Why don't you put it in the chat if you've got an answer for me? Then you don't have to. What do you think? What's the heat of melting? How many calories does it take to melt 1 gram of ice? I got my eye on the chat here. If you've got an answer, you could raise your hand or just blurt it out. How much heat does it take? 80, says James. That's a really good guess. It actually takes about, did I say 80? I looked at 100 and I said 80. That's because it takes about 80 calories. And what that means is it takes 80 calories to convert 1 gram of 0 degree ice to 1 gram of 0 degree liquid without even changing its temperature, right? Just changing its phase. Now, I assume that you learned that before, obviously in a chemistry class, but maybe you learned that in joules and you were having trouble converting it. When you can convert that, just multiply 80 calories by whatever 4.187 joules per calorie, and you're going to come up with a number in joules. So you can look up that number and memorize it if you want. I'm using calories because the specific heat, when you express it in calories, the specific heat of liquid water is 1. And so you can easily see that this is 80 times bigger. Right? Does that make sense? So, if it takes you, 10 minutes to raise the temperature of some amount of water by 1 degree, 80 minutes. Did I say that? 8 minutes? 80 minutes is going to take you 80 times as long to melt it. So this is huge. This is a huge amount of heat. You thought the specific heat of water was high. The heat of melting is huge. It's really hard to get solid water to let go and become liquid water. All right, what about this one over here? Let's say we want to convert liquid water into vapor. Obviously, this is called the heat of vaporization. If you're going from left to right. If you're going from right to left, it's called the heat of condensation. I didn't spell that right, but right. If you go the other way, it's called heat of condensation. Do you think that it takes more heat to vaporize a gram of water or more heat to melt a gram of water? Is this going to be bigger or smaller than 80 calories? I want everybody to just make a guess If you think it's bigger, give me a check mark. If you think it's smaller, give me an X. And we'll just see how what people are voting here. Where's my list here? I've hidden all kinds of things in my Zoom today. Hey Jeff, can you watch? Jeff's gonna go. Jeffrey. All right, which do you think? Do you think that the heat of vaporization is bigger? Give me a check mark. Or you think it's smaller? Give you an X compared to the heat of melting. Or in other words, which is greater, the heat of vaporization or the heat of melting? We got a more, we got a greater and a greater, got a bunch of X, got a bunch of check marks, a couple of X's. And the answer is, it takes even more heat to evaporate a gram of water, right, to convert it. It's on the order of 680 calories. I'm going to write 679 calories because that's, I'm pretty sure, the number Cal fused. 680 calories. So we're talking more than 8 times as much heat as the heat of melting. Almost 700 times the specific heat. This is huge. And what that means is that it takes more heat to evaporate a gram of water than it takes to raise 0 degree water all the way up to 100. It takes almost 7 times as much heat to evaporate 1 gram of water compared to the amount of heat it takes to raise its temperature. So you thought that the specific heat of water was high. Man, the heat of vaporization is incredible. It sucks up a lot of heat to evaporate water. Now, you could force water to evaporate by changing the air pressure, or force it to condense by raising the air pressure. And that's how a lot of clouds get formed. When air is forced up high into the air by air pressure differences, if a parcel of air rises into the air so that the air pressure decreases, that decreasing of the air pressure causes evaporation of the water, which sucks the heat out. If you force air to condense, did I say that wrong? Okay, wait, anyways. I'm getting all my ups and downs, my lefts and rights mixed up today, so maybe I'll stop talking that way. Let's go back to specific heat. All right, you know that the specific heat of water, if I can draw this here, right, is one calorie, per gram per degree C. I don't really know how to do superscripts in Zoom annotation, so I'm just going to write it like that, right? That's the specific heat of water. It takes 1 calorie, or whatever, 4.187 joules, to raise 1 gram by 1 degree C. What is the specific heat of ice? Does anybody happen to know? What's the specific heat of ice? Is it the same? Is it more or is it less? How much heat does it take to raise a gram of ice 1 degree? Like, from minus 10 Celsius to minus 9 Celsius, or ice at 0 Fahrenheit to ice at 1 degree, I guess 2 point, okay, never mind, let's stick with Celsius. Does it take more heat or less heat or the same amount of heat to raise 1 gram of ice 1 degree? More, less, or the same? You can put that in the chat, more or less or the same. I got my chat open, so I want to see, what do you think? Is the specific heat of ice, in other words, more, less, or the same as the specific heat of liquid water? Looking for some opinion here. Less, more? So massive disagreement here. The answer is, it is less. It is about, I'm just going to give you an approximate number. It's about half a calorie per gram per degree C. And we're not going to talk about water vapor because it's much, much more sensitive to pressure. And we don't really deal with a lot of water vapor in limnology, but we deal with solid and liquid. Okay, so these are some really important properties of water, which all relate to heat. And you know, heat is energy. Heat is the kinetic energy of molecules. And it takes a lot of heat to raise the temperature of an ice cube by even a degree, you know, even 1 degree. It takes even more heat to raise the temperature of a glass of water. It takes a lot more heat to melt an ice cube, and it takes a huge amount of heat to evaporate that much water. So that's what these numbers represent. Okay, so I'm gonna close some of my things here. Do I want to save that? No, you've written this down if you wanted it. Okay, so I'm gonna clear all my drawings, stop annotating, and go to another slide. All right, so let's talk about what water is. Let me just remind you, water is H2O, right? We got an oxygen molecule and 2 hydrogens. And oxygen is very strongly electronegative, which means that even though it is sharing electrons with the hydrogen, if you can see this, it's sharing the electrons with the hydrogen. So the electron clouds that those electrons form are denser on the oxygen side. The electrons that are shared between the oxygen and the hydrogen, those shared electrons that define the covalent bond, those electrons actually spend slightly more of their time around the oxygen. And because they spend more time at the oxygen, this in effect gives the oxygen what appears to be a slightly negative charge. And because those shared electrons are spending less of their time around the hydrogen, this has the effect of giving the hydrogen something like a slight positive charge. And this would be like, you know, like a static electricity kind of thing. You know, like it's sort of a little bit negative on one side, a little bit positive on the other. So we say that water is a polar molecule that has kind of a positive side to it out here and kind of a negative side to it. Now, when you think of water in a liquid state, these molecules are in constant motion. But in any given instant, they tend to be oriented so that the negative side of one molecule will be facing the positive side of another. And the slight static electric kind of attraction between them is called a hydrogen bond. Now, it's not really a bond. There's no sharing of electrons. But there is a slight attraction between them, a slight force attracting them. Now, the problem is we're talking about a liquid. And what that means is these things have kinetic energy and they are constantly rolling around, bumping into each other. You know, they're slightly attracted to each other, but on the other hand, they're constantly in motion. So they're never actually touching. And they're spinning constantly and like slopping around, sloshing around, flying around. But it is this attraction between the molecules that gives water so many of its important properties. In order to raise the temperature of the water, which basically means making the molecules move faster, the problem is they're constantly slowed down by their attraction to each other. So if you added heat, which essentially would increase the velocity of these molecules, some of that extra energy is sapped away by the attractions between the molecules. This is what creates the high specific heat of liquid water. It's very hard to get water molecules to move faster because they're constantly attracted to each other. So the high specific heat of water is caused by the attraction of water molecules to each other. This is also what creates the high viscosity of water. And the viscosity of water is if you have a bucket of water and you try to move the water at the top, it's kind of hard to make those water molecules move because they're attracted to the water molecules beneath them, which are attracted to the molecules beneath them, and so on. And because water molecules tend to, in a sense, stick to each other, you know, cohesion, this leads to a high viscosity. You have to constantly put energy in if you want to make something move through the water. So that's these so-called hydrogen bonds, which are not a bond at all, really. They're just an attraction between molecules caused by differential distribution of charge on their surfaces. Leads to not only the high specific heat of liquid water, but also the high viscosity of water, and also the high heat of vaporization. It's over here we have gas, water molecules in the gas form. You'll notice there's no hydrogen bonds over here. That's because this is a vapor, this is a gas. These things are moving too fast for the attraction between them to make any difference whatsoever. They effectively hit each other and bounce off like billiard balls or on a pool table. And they're moving at a higher velocity and they're no longer attracted to each other. But to go from this state to this state, you have to put up enough energy to make these molecules move fast enough that as they go flying by each other, the static attraction between them is insufficient. Now, if you add this heat, not only are they flying, they're also rotating. And that's another part of the decrease in the attraction between them because, you know, you don't always have like the positive side facing the negative side of another one because each molecule is spinning also as it's flying around. So these so-called hydrogen bonds are also responsible for the very, very, very high heat of vaporization of water. Now, the heat of fusion of water is a little more complex, but I would say if you think of water as a solid as being crystalline, and what we mean by that is here you've got a whole lot of water molecules and they are very, very neatly arrayed in these quite spacious, open, hexagonal structures, right? So each little red spot that you see is the oxygen of a water molecule. So here's a water molecule and here's its two hydrogens. And it is directly lined up with the hydrogen of a different water molecule and so on. And you get this hexagonal shape. In water, the average distance between the oxygens, the oxygen atoms, the average distance between them is higher. They are farther apart than in liquid water. In order to go from this liquid water state to the crystalline ice state, the water molecules actually have to move away from each other. They have to move farther away from each other and rotate and then settle in to this structure. This is why ice has a lower density than liquid water. And this is why water at 1 degree has a lower density than water at 4 degrees. In between 4 degrees and 0, the water molecules have to move apart from each other as they start settling in towards this crystalline structure. This is why water has a maximum density at around 4 degrees. like any other liquid, you know, as it cools, the molecules get closer to each other. But unlike other liquids, because the solid form is so much less dense, there's kind of a turning point. And as it starts getting really close to the solidifying temperature, 0, they have to move apart from each other. And so they break away from the normal behavior of a liquid. Now, this is not true when there is salt in the water. We're just talking about pure, 100%, absolutely pure water. You throw a solute into the water and it changes things. Because if you threw a bunch of, you know, sodium ions that were positive, then the water molecules would orient around it. And if you throw some chloride ions in the water, other water molecules will orient the other way around that. And that changes the whole like density temperature thing, because it disrupts the effect of these so-called hydrogen bonds, because the electrostatic attractions, instead of dominating the interaction between water molecules, is taken over by the solute. All right, so this is all sort of a picture. I'm putting into words things that I'm sure you have learned before, probably in other words, you know, chemistry kind of words. So let me show you what the effect that this has. All right, what are the effects of this? All right, here's a graph. I'm pretty sure this is from the textbook. Oh, and I'm focusing in on a piece of it. On the x-axis, we have water temperature. On the left, we have 0 degrees. On the right, we have 10. 10 Celsius is about 50. You know, so that's kind of a cool outdoor temperature. And what you can see is that as you go from 0, the density of the water increases up until around 4 degrees. Now, in pure laboratory conditions, this would be, you know, whatever, 3.97, 3.94. Water in nature is never distilled water. So this actually tends to be a little bit below that, but we're just going to say 4 degrees, because it does vary a little bit even in natural water. So I would say 4. If you happen to say whatever, 3.94, 3.97, I'm not going to say that's wrong. But just bear in mind, in nature, we never deal with pure distilled water. So that's the temperature maximum density. Maximum density of water at ordinary surface, 1 atmosphere pressure, you know, is about 99.99 grams per liter, or 0.9949 grams per cubic centimeter or milliliter, or 999.99 kilograms per cubic meter. A cubic meter of water, which is maybe a volume you would deal with talking about lakes, a cubic meter of water weighs 1 metric ton. A cubic meter of water, if you can picture that, a cube that's 1 meter on each side, picture that water, liquid water, it's going to have at its maximum a density of 999 kilograms. In other words, almost a metric ton. A metric ton is 1,000 kilograms. A metric ton is a megagram. Okay. Like any normal substance, any normal liquid, as you warm it up, the molecules get farther apart from each other on average, and the density drops, therefore, of the liquid. So that's what you're seeing here. Well, how does the density of ice fit in? Well, what I showed you before was this top part of the graph up here. Zoomed in, maximum density at about 4. As you warm up above that, the density decreases. But as you go from 0 degree liquid to 0 degree solid, the density makes a huge change. It goes from about real close to 1 gram per liter to about 917 grams per liter. In other words, it decreases in density by like 7 or 8%. It's huge. So this is the density of liquid water at 0. Here's the density of solid water, ice, at 0. Now, ice is a solid, and once the water is a solid, it's a fairly normal solid, which is to say, if you take a solid and you heat it up, it expands. If you take a solid and you cool it down, it gets denser, it contracts. And so you can see that as you cool the ice, this is gonna work. As you cool ice down, it gets denser because it's a normal solid. But even so, even if you've got, here we got 150 degrees below the 0 Celsius, which I think is pretty close to the coldest temperature ever recorded on Earth. Actually, that's pretty far, it's below it, somewhere down in here. Coldest temperature on Earth ever recorded. That ice is nowhere near as dense as even hot water, which would be over here. Right? So even if you took water right up at the boiling point and compared its density to ice at the coldest you'd ever see it on the surface of the Earth, you can see that ice is never going to be more dense than water. Now we can see that. Okay. But you throw some salt in the water and everything changes. Now, seawater is not the saltiest water on Earth, but it is the largest volume of water on Earth, so its saltiness is pretty important. In 1 liter of seawater, there's about 35 grams of salt. And you can make salt by taking seawater and evaporating the water off. Just evaporate the water out and you'll be left with the salt. Of course, you're going to be left with, the algae and the other stuff that's in the water, but most of the dissolved solids in seawater are sodium and chloride. And there's about 35 grams of that, sodium chloride, in seawater. Things like the Great Salt Lake, much saltier. But, seawater, about 35 parts per thousand, 35 grams per liter. What does that do to the density of the water? Well, it makes water denser, right? So here's the density, and you'll notice these densities are all greater than 1, whereas pure water at its densest was slightly less than 1 gram per cubic centimeter, or kilograms per liter, or whatever you want. And you'll also notice that not only is seawater denser at all temperatures, there is no longer a maximum density above the freezing point. The freezing point of seawater is a little bit lower than the freezing point of fresh water. You have to remove more heat to make it turn into ice. The freezing point of seawater is about 1.9 degrees lower than the density of fresh water. All right, click on the wrong thing here. So right here, we've got a temperature of, get my annotate thing here. Anybody happen to know what the freezing point of water is when it is seawater? It's a little bit less than -2, and the number is typically given as -1.91 degrees C for the freezing point of seawater. Right? And you can also see that there is no maximum density above the freezing point. And that's because of the way the ions, the positive and negative ions that are the sodium chloride ions, interact with the polarity, you know, the partial charges on the surface of the water molecules. Now, do icebergs actually freeze at negative 1.91 degrees? The answer is no, actually, because the salts are not evenly distributed throughout the water. And once an iceberg starts forming, as additional water freezes to the outside of it, the formation of the water crystals tends to exclude the salt. So an iceberg, which forms from freezing seawater, is actually fresh water. That during the formation of the ice crystals, the salt ions keep getting pushed to the outside and pushed to the outside and pushed to the outside, so that the ice itself is pure seawater, pure water, and right outside it is kind of a salty film of extra salty water. This happens when you freeze fresh water too. If you have a bunch of crystals of ice growing in fresh water, and they're kind of growing in all directions towards each other, you'll actually get sort of crystals of pure water with films of very salty water around them, which is part of the structure of lake ice. In any case, you can see that seawater is a normal liquid. As you heat it up, adding more energy to the molecules, they end up on average farther apart from each other, which lowers the overall density of the water. All right, I think, is that my, whoop, and my, that. I have mentioned the viscosity of water. This is an interesting property of water. It is probably not that important, I think, for our purposes. It is important, however, if you're a tiny little creature. If you are a tiny little creature in the water, trying to swim through the water. In order to swim through the water, you have to push some of the water molecules away. If you swim through the water, you're going to push water molecules away. If you're really small, the resistance of those molecules to moving could be a big deal for you. And so, you know, you can see these things like copepods and Daphnia. When you see them swimming, what you'll notice is they don't glide. When you see Daphnia or copepods in water and they swim, they have a very powerful swim that they do with their antennae. They swim. That pushes them forward and then they stop almost instantly. They push and they move, but then they stop. There's an enormous resistance caused by those water molecules cohering to each other. And that's what viscosity is. Viscosity is the resistance of a liquid to deforming at a particular rate. You know, like if you want it to move fast, it's going to take a lot of energy to make it move fast. That's viscosity. If a liquid, on the other hand, has a very low viscosity, it's pretty easy to push through it, or conversely, to push it through like a small hole or something. So the units of viscosity are pressure, like newtons per square meter, or pascals. 1 Pascal is 1 Newton per square meter. So that's pressure. And pressure is force per unit area. And the other part of the units of viscosity is time, seconds. So if something has a high viscosity, then it takes a lot of pressure and a lot of time to move it a distance, or to move an object through it a certain distance, or to move the liquid past like plates or through a hole in the surface. you can get a feeling for viscosity by putting a liquid into a syringe, like a plastic syringe, and then see how much pressure does it take to force the liquid out the nozzle. If a thing has a high viscosity, like honey or molasses, it takes a lot of pressure and a lot of time to move the liquid through the nozzle of a syringe. If you have a really thin, a low viscosity liquid, like gasoline or something like that, it's really easy. It doesn't take much pressure or much time to force it through the nozzle of a syringe. So if you think of viscosity that way, I think you'll have an understanding of what it is. The units are pascals times seconds, or newtons per square meter times second, pressure times time. And I think, as you can imagine, if you heat water up, if you make the water warmer, the molecules are moving faster, they are farther apart from each other, and they are less influenced by the static attraction that we call, static electric attraction that we call hydrogen bonds. And the viscosity drops off rapidly as temperature rises. Now, I got this graph from Wikipedia, so the temperatures are in Kelvin. It's a good looking graph, but maybe a little hard to interpret these temperatures directly. Here's temperatures of water at some realistic temperatures. 10 degrees Celsius, that's like 68. 20 degrees, sorry, that's like 50, sorry. 20 degrees, that's like 68. 30 degrees, that's like getting hot. So when you're talking about lakes and lake water, you're talking about a range of temperatures that's kind of in here. 25 is maybe the warmest you're ever going to see water, maybe 30 in the tropics. But you can see that the viscosity drops from like about 1.3 down to about 0.8, which is not quite dropped in half, but it's kind of heading in that direction. It's about 70%. 70%. Well, anyways, this is about 1.7 times that number, so 170%, but not quite double. Anyways, substantially less in like tropical water compared to cold water. And most of the difference is actually in right near, because you can see this is very steep here, a steep curve, and it's less and less steep as you go on. The biggest effect on viscosity is at the coldest temperatures. If you were a tiny little thing like a copepod or a daphnia, then yeah, I think viscosity would matter to you. It's easier to swim in the summertime if you're that tiny. If you were a fish swimming through the water with your mouth open, hoping to get water past your gills because the water's carrying the oxygen. Yeah, I think the lower viscosity in the summer does make it easier for you to swim, and it makes it easier for that water to flow past your gills across the rough surface that is the gills. But if you're a fish, it's probably more important that cold water holds more oxygen. So I think if you had a choice, you'd probably choose the cold water, even though it's harder to swim and it's harder to get it over your gills. So, okay, so that is viscosity. I think generally speaking, people don't tend to have a real good sense of what viscosity is. Viscosity is not strongly connected. It is not strongly connected to density. The density of a liquid does not predict its viscosity. Density and viscosity are two different things. Density is about mass per unit volume. Viscosity is about the stickiness of the molecules to each other. Okay, sticky is not a great word because typically we use the word sticky to refer to the adherence of molecules to other substances. Like the fact that honey sticks to your fingers is unrelated to its viscosity. the fact that honey sticks to honey is its viscosity, is what affects its viscosity. Nevertheless, sometimes people find it useful to divide the actual viscosity by density. And so you will see one definition of viscosity, I think it's called dynamic viscosity, which is true viscosity divided by density of a substance. We're not going to talk about that. I want to just emphasize that density and viscosity are really two completely different properties. There tends to be a correlation between them because both of them decrease with temperature. If you heat water up, its density decreases. If you heat water up, its viscosity decreases. So they are correlated to each other because they're both affected by temperature. Okay. And I wanted to, okay, I want to stop hitting the wrong button here. Go find my annotate key, my annotate clear. All right, do you have any questions about any of these properties of water that I have just belabored or just explained, reviewed, gone over? Any questions about the properties of water? All right. Well, what I'm going to do now is I'm going to send you back to your discussion, your breakout rooms. You know, I can't see your faces, so I don't know whether you were like awake or sleeping, whether you were like taking good notes or whether you were, you know, staring off into space, which is like the problem of teaching on Zoom. But I'm going to assume that one way or the other, you're ready for the next question. So I'm going to send you back to your discussion groups, and I'm going to ask you to answer this. You now have all the information you need to answer these more expanded questions. First of all, why does ice float, and can ice sink? I have a friend from Wisconsin who tells me that every spring the ice sinks, and she's seen it. Okay, so is that possible? Second of all, why is it cooler by a lake in the summer? And is that also true in the winter? Why or why not? Why do lakes stratify in the summer? And can tropical lakes stratify? How about Arctic lakes? Why or why not? And of course, the big question, which properties of lakes are the most important for life in lakes and why? Now, I took this question and I called it today's second question. And I did post a copy of this on D2L just as a Microsoft Word file in case you want to have access to these questions when you're in the breakout rooms. So I'm going to give you time to discuss this in your breakout room, or I could make new ones. Do you guys want the same rooms, or you want me to mix it up and have some new rooms? If you want to keep the same room, give me a check mark. If you want to mix it up, give me an X. And the first couple of people to vote get to decide for everybody. And I got 2 let's mix it up votes. I got 2 saves it. Oh, I got 4 mixes and 2 saves. So let's have Zoom mix it up for you. And oops, how am I doing that? Breakout rooms. Let's see, we had 4 rooms. Let's see, we're gonna recreate rooms. We're gonna have 4 rooms of 4 people each, except the room with, you know, Jeffrey, who doesn't help much. Okay, so please answer these 4 questions. It looks like 10 minutes wasn't quite enough time, so I'm gonna give you 15 minutes, okay?
All right.
Hello.
No.
Okay.
Catherine or anyone willing to share their screen and type up these answers?
Yeah, I can do it again.
Thank you.
Yep.
Okay. So why does ice float and can ice sink? Okay, so the initial density answer is correct. That is why. But can it sink? I guess yeah, it can then, right?
Uh,
Did I if I understood the lecture properly, it can, depending on the temperature?
Well, because it's like she was talking about how ice can become more dense the colder it is.
Yeah.
It's like
Well,
this.
I thought it became yeah, it becomes more dense.
Yeah.
And at some point, it could be denser than water and then sink. So
Yeah.
yeah, ice
Well,
can.
didn't she say though that that couldn't happen?
Yeah, I don't think it can sink. I think no matter what, I think just based on how the bonds work and the polarity, I don't think ice can technically ever sink.
Yeah.
Fresh water, that is, I would imagine.
But that was
Maybe,
just because she
maybe
was
what,
talking about like the how you can boil water at like the highest point or something, and how that still doesn't compare to ice at its highest point of being dense, being even close to being denser than water.
oh, yeah, okay.
Okay, so then it can't. No, then.
Okay. Next one. Is it also true in the winter? Why?
So I know for the summer she explained when we went through it the first time, she was just saying that because the land and the water heat up at the same rate, it's just that water mixes, so the it gets, I guess, more spread out in the depths of the water, so the lake stays cooler.
Yeah.
So that when that breeze comes through, it cools off the inland part of the, or the less inland part of the land. Um, so I would imagine it would be the same for the, well, shit. Now I'm trying to remember the lecture or what she explained that part with winter.
Well, I don't know if she did explain the winter part, but if you just think about the ice and how the ice doesn't move during the winter time.
Yeah, because see, like Keenan made this point in the chat. I always heard that it's always a little warmer by the lake because, and I would just assume it's because the light's reflecting off the snow and the ice. So it's like hotter above like the ice and stuff. But
Okay.
that's just me spitballing what I would assume of why they would tell me that.
Okay.
So so we know why the summer, we can explain that part, but yeah, I don't think she really went over the winter part at all.
Okay. Yeah. Because I mean, the water underneath the ice layer is warm. There is water that is like that's warmer than land.
Yeah, because I think what it's going to be from what I remember from Unit 1, it's just going to be a solid or a consistent 4 degrees Celsius.
Right. Did you guys want to go to the next one?
Yeah.
Okay. Why do lakes stratify in the summer? Can tropical lakes stratify Arctic lakes? Why or why not?
Not gonna lie, this is the part where I kind of zoned out when we were talking about the density of salt water.
Yeah. No, she lost me on the salt water, and then the viscosity I'm still a bit confused about. Um, yeah,
Well, I mean, the viscosity part is just the colder. Okay, so viscosity and density are correlated, but they
right.
are not the same thing. And as the colder it gets, the more viscous the water becomes.
But it has higher oxygen, so fish like it more.
So fish would prefer it more. Yeah, that's what she said. At least
Right.
that's what I recall from that. But I don't know. Is that like
That's not related to this at
this
all, but
question? Yeah, yeah. So why do lakes?
So during the summer, it has to do with that the warmer top layer is less dense, so the colder water sinks to the bottom, and that's how you get the two distinct layers of stratification. But yeah,
Okay.
I just got lost with I got lost in the salt water and the density of that part of that lecture. So I kind of missed if tropical lakes stratify or not.
I don't know. Did she even mention that? I don't remember recall it.
Well, do tropical lakes have salt water? Do they all have that? I guess they would.
I just figured I just thought with the tropical part she
Yeah.
meant by salinity, but I could be just adding that part for no reason. So
Well,
yeah, that's a good point. It
if
could
it
just be a temperature thing.
yeah, but if it did have salt water, the salt water would sink to the bottom, and so then it would be harder for that to like mix. Right? Because if the salt water is denser than non-salt water. I don't know if I'm saying this right.
I don't know. I mean, I feel like I need to read. I need to read. I haven't read the chapter yet, so I need to read it.
Yeah.
I guess we can skip this one for now.
Okay.
Yeah.
Would you gut feeling? Would you guys say yes or no to this one?
I guess I imagine because it has to do with like a temperature thing. I think that tropical lake would probably stratify like longer and more
Yeah.
because the heat would be more intense. And then I feel like in the winter with Arctic, because I'm trying to think in Minnesota, if I look at my notes, does the lake stratify in the winter? Because if the lake stratify here during the winter, then I would imagine more so in the Arctic too, right? Just because well, I mean, shit, we're in a polar vortex, so it's probably just as cold as the Arctic up here now.
Oh my god. Cannot. No. That's not how you're supposed to ratify. Yeah, no, I would agree with tropical. I would say tropical, those ones would stay stratified for longer. Because if you look at the lakes, for example, in Africa that she was talking about that one time, or else just like even deeper lakes in general, but lakes that are in tropical areas. Because if it's tropical, then year round, it's at like a nice 70 degrees. And so if it stratifies in the summertime for Minnesota, and that only takes 3 months, I'm just thinking that it would stratify in tropical areas, but because they'd be stratified for a period of time because there's not much that's mixing it up, then it would be harder to de-stratify it because there'd be a bigger difference in temperature.
Yeah, I just did a quick Google search, just like repeating that question. The only thing I really found on a quick thing, not looking too much, it just says that lakes in the Arctic are often cold monomictic, so that just means they stratify once, in the, they have that one thorough stratification
Yeah.
or mixing, I guess. So I don't know if that means that because of that mix, it will just have a consistent mix, or if then it will settle and stratify. So I don't know if that's really helpful, but
Yep. We're gonna go with that. I would say yes to both. But I don't know. I would say that probably tropical would be more difficult than the Arctic ones. But I don't know. That's what I would agree. And then the big question, which properties of water are most important for life? I'm surprised that our group was the only one that really talked about that one.
yeah.
Or just said what you said. So I hope that's okay.
Yeah.
But yes. Did anything else pop up? I don't feel like salinity is really that important.
No, salinity didn't. It was pretty much just the high specific heat,
Yeah.
the polarity, and then and then I think that's where she was talking about the viscosity being pretty important.
Yep. Yep. Well, did anyone else have anything to add or any other ideas for any of the other questions?
I don't got nothing. No.
Yeah, I think back to the Arctic lakes. I think because it's so cold, I think it would be. I just kind of skimmed the notes you jotted during her explanation. So it said the greater the difference in temperature, the more density, which means the harder to mix. You know what I mean?
Yeah.
So I would imagine that Arctic lakes would be less stratified because it's going to be a consistent, 4 degrees. You know what I mean?
Yep.
Celsius. So it would be more like the more mixing, I guess, if it wasn't for the ice layer. Because I'm assuming Arctic lakes are frozen over longer.
Yeah.
So I would say less stratified. Less stratified.
Okay. And that's because you've got an ice layer on top.
Yeah, I would just say because it's a more consistent temperature throughout the whole body of water.
Oh, okay. Yep. Yep. Yeah. Whereas for like tropical, it could be like 30 degrees. And I'm talking Fahrenheit at this point, but 30 degrees of like one part, 32 degrees of, one part of it, and then like 80 degrees at the top of it, or
Yeah,
70 or whatever.
yeah, that temperature could be drastically different, especially with that heat coming in on it. Did any of you all check your grades on your midterms yet?
Yeah.
I have mine. Yeah.
I haven't checked it yet, but I hope it's all right. I'm
Uh,
afraid to look. I didn't leave too nervous, but I didn't feel the most comfortable either, if that makes any sense.
Yeah. I walked out of that test a lot more confident than when I saw the grade. And so I'm a little sad about it, but it's okay. We'll bounce back. I
well, if
don't
it
know.
makes you feel better, last semester when I had ecology with Virginia, everyone did a lot worse on the first test than the last two.
Hey,
Yeah.
that's good to hear.
Yeah.
Yeah, I felt like that was like I said, whenever with a professor like Virginia, it's nice to now I have a better idea of how her tests are gonna go, like how she asks questions and stuff,
Right.
and the details of what I need to know. There were a couple things on that exam where I was like, oh shit, this is like one of those micro details that I completely blew over.
You know which one I was really happy that I did? Like I know for sure that I got it. It was the one where it asked what was the one federally endangered fish species in Minnesota.
Yeah,
I knew that one, and it
they
was
I
because I
forgot
watched a lecture.
I forgot the name I was like, I'm pretty sure it's a minnow and I know the region. I just can't tell you the species name. I just
Yeah,
know what type of fish it is.
yeah. It was the Topeka shiner.
The Topeka Shiner, damn it. Because once I saw that question, I was like, yep, all I got is that it's a minnow. That's all I
Yeah,
could tell you.
yeah. So, yeah, I was amazed that that was even in there, but I was also amazed that I knew it.
Yeah, but then when you saw that, you felt good as hell. You were like, hell yeah.
So,
You were like, minor details, baby. Minor details. Let's go.
and then I thought I knew everything else, and I didn't. But it's okay. It's okay.
Yeah, I mean, I'm glad though that she allows us to record these lectures. That's huge.
Yeah.
Because one
I
of my
mean, it would be really difficult if it wasn't
uh
allowed.
like one of my classes, my professor's on point with recording them. One of my professors doesn't allow us to record, but she doesn't post them. So I'm like, what the hell?
What do you mean she doesn't allow you to record? What the hell?
Yeah, like she doesn't allow us to record the lecture. Like she records them and then she claims she's gonna post them and then she never posts them.
Which professor is it? Oh
Suzanne
no, no.
Magdalene,
I had her last semester. She was the worst.
dude, it's a dumpster fire.
Yeah, it was a mess of a class. During our midterm, she gave us questions while we were taking the midterm that she forgot to add on. So she was adding to it while we were taking the midterm. We didn't get anything
What?
graded at all. By December, it was like I didn't have any grades in the grade book, and I didn't know if I was passing or not. And I think she just graded all of us based off of how she liked us. So just Bite your
What
tongue.
the
and
hell?
They'll
Yeah.
like you, and this will give you a good grade.
Did you get some answers? Come up with some questions? Let's see, do we have everybody back? Okay, we got everybody back. All right, well, let's start with, we got 4 rooms and 4 questions. So let's just start with room 1. That'd be Bree, Jeng, Sam Thomas, and Saul. What do you think? Why does ice float and can ice sink? What do you think? So that'd be Bree, Jeng, Sam Thomas, and Saul.
So ice is denser or less dense than water. That's why it floats. And then we talked about this a bit. We do not think ice can sink.
And why not?
Because liquid water is just always going to be more dense than solid water.
Yep. At ordinary 1 atmosphere surface of the Earth, liquid water is always more dense than solid water. And even if you try to imagine things like air bubbles in the ice, well, that's just going to make the ice less dense. Or seawater, salt in the water. Well, that's just going to make the liquid more dense. So really the only way that the ice could sink would be is if it had a lot of sand in it or something, So really, realistically, no, not if it's pure water, for sure. All right, good job. All right, let's go to room 2. That'd be Keenan, Sam, Pitdorf, and Tiffany. Why is it cooler by a lake in the summer, and is that also true in the winter? Why or why not?
So we discussed that about the wind in the summer mixing the water. So for the winter, we said no because there would be ice blocking it.
Yeah.
So not any heavy mixing.
Yeah, the key reason that it's cooler by a lake in the summer is because heat absorbed by the surface gets distributed throughout to some degree throughout the depths of the lake, even if the lake is stratified. The specific heat of dry soil is about a quarter the specific heat of water, liquid water. The specific heat of dry soil is about a half the specific heat of ice. Of course, soil is never totally dry. And if the soil is wet or saturated, if it's like a 50-50 mix of dirt and water, that's going to bring its specific heat even closer. And if the ground is covered by snow and ice, well, that's water. So in the winter, there's 2 things going on. First of all, the specific heat of the land surface is probably very close to the specific heat of ice. So they're not very different. And then neither of them is really able to convect and carry the heat away from the surface. Now, it's possible that a lake, some heat is going to make it down into the water, and there is convection under the ice of a lake. So it's at least theoretically possible that it could be a little cooler near a lake in the winter for that reason, because of heat being carried down. The ice has some thermal, and there's theoretically possible that there could be some effect. But remember, you'd be comparing ice to frozen ground. So theoretically, but it's going to be small, I think. All right, room 3, nice job. Let's go to room 3. That'd be Brett, Desiree, and Ju. Why do lakes stratify in summer? Can tropical lakes stratify? How about Arctic lakes? Why or why not?
We said tropical lakes would stratify, but Arctic lakes wouldn't.
Okay. And why wouldn't an Arctic lake stratify?
Because there'd still be ice on the top.
Okay, yeah. And you go to the extreme high Arctic or Antarctica, and lakes may be ice covered throughout the summer. There might be just a moat of open water around the edges. Yeah. And if the entire water body is below 4 degrees, it's not really going to stratify because the warmer water near the surface is not going to be less dense. So the water really does need to be above 4 for it to stratify. So I think that's a good answer. Good answer. All right, room 4, you got the big question. Abdul and Dolly, James and Kat, what do you think? What properties of water are the most important for life in lakes and why?
Yeah, so for this question, I think we're sticking with the specific heat answer that we had before, but we also added on viscosity.
Oh, okay.
So we had those two as pretty important properties.
And why the specific heat?
That's again because when the ice forms on the top, then it makes sure that the fish can survive underneath. So it still has that environment for fish to live in. And it's like the ice layer is protecting them. And then you've got the water that's underneath the ice that's happening.
Oh, so you're talking about the density.
Okay, density. Sorry about that.
Yeah.
Density and then viscosity.
And then why do you think viscosity is important?
Viscosity, just because it was brought up that if colder, like fish like colder water because it holds more oxygen to it. And so it was like the oxygen aspect of the viscosity that seemed important for that one.
Okay. All right, yeah, I'd have to think about it. I don't think that viscosity is related to, it causes the oxygen holding content capacity. That's more like Henry's law, but I would say certainly the oxygen holding capacity is important. All right, yeah, and the temperature, the relationship between temperature and density is obviously very important. That explains stratification of lakes at the warm end of the scale. It explains the floating of ice in the middle. And, well, I guess it's probably not that important that ice shrinks as it is cooled below the freezing point, although that explains a thunderous booming of lake ice as it cracks on cold winter nights. Just probably not that important, but is kind of cool. The thermal capacity of water is another kind of set of properties. The very high specific heat, the very high heat of melting, and the very, very high heat of vaporization really mean that water stays fairly stable in temperature and doesn't change rapidly from day to night. It also means that water on Earth is liquid most of the time. And that's obviously really important. So the whole sort of package of properties related to the relationship between heat and temperature and phase, solid, liquid, gas, that package of properties is obviously very important for life too. And I would go for viscosity also because I work with little unicellular organisms that fall. And if the water was an extremely thin, low viscosity thing, it'd be a lot harder to be plankton. So, all right, well, it is time for our halftime break. So we're going to take a 10-minute break, and then we're going to come back and talk about light in lakes. Yeah. Okay, so I will see you all in 10 minutes. Take a break. as a class, you did really well. And I was pretty pleased. I thought that went really well. And usually the first exam is the hardest because there's has the lowest average, because there's always some students who didn't, now they know what they need to study. They're like, oh, I get it, or now I know what she wants. So there's always some students who do much better on the second and third exam because, they just kind of learned something about what I was looking for. So the fact that the first exam was really pretty good, to me was very promising. I think as a class, you guys are going to do fine. I don't know how you feel individually. You may have had higher hopes. I know one or two of you totally blew one question or something and it lowered your whole score, but most of your test was really good. So when you get it back, be sure to look it over. Am I answering all those questions? We will be meeting at the Lake Phelan boat launch parking lot. That is in between Phelan and Round Lake. If you want to just park where you parked last time, you can walk across Round Lake to get there. Or you can walk over the little footbridge on the footpath. If you want to drive closer, you drive beyond that and you take your first right-hand turn around the circle and then your first right-hand turn to get into the boat launch parking lot. And there is plenty of space there. If everybody gets there, it's fine. If for some reason it's full because people are ice fishing, there's another little parking lot right on the way that you go past. So we're going to be meeting in the little parking lot in between Round Lake and Lake Phelan. You could see last time where we're going to be this time. Other questions? It's going to be fun. I think it's going to be great. We're going to look at zooplankton, which is the lab that we postponed. And we're going to look at aquatic plants, which is the topic we're going to start in on next week. So I think it's just going to be beautiful. It's going to be a lovely day. You're going to feel like it's spring because it's been so cold and it's not. It's going to be great. You're going to be glad you're not in Texas. I just feel really happy about this. I think it's going to be great. All right, let's talk about light in lakes, which is a topic that directly connects to the second of these two labs, Lab 4, light and the littoral zone. All right, so let's start out with what is light. And to do that, I want to just show you some little PowerPoints. If I can, oops. Oh, so much going on. I'm going to close that PowerPoint. Open this one. There we go. Okay, got my little agenda here. Okay, lights. What is light? What is light? Okay, here we go. All right. What is light? Light is waves of electromagnetic energy. This is a diagram from CALF, the textbook. Light is waves of electromagnetic energy. As you know, there are really only two things in the entire universe: matter and energy. Matter is stuff, it has mass. Energy is not. Everything in the universe is matter or energy, and energy does not have mass. It's just energy. Like if you see a wave rolling across a lake, the water molecules are not moving all the way across the lake. The energy is. And that's kind of a hard concept, but just work on it as you go through life, and someday it'll make perfect sense to you. Oh, Jeffrey, what happens? Of course, if you get down to teeny tiny little quantum levels, it turns out that actually matter and energy are not different from each other, because that's how like atomic bombs work and stuff, right? Is if you convert matter into energy, you find that even the tiniest amount of mass you can imagine is actually a huge amount of energy somehow spinning in a teeny tiny little point in space. So it turns out actually, if you get to a really, really fine scale, that matter and energy are the same thing, which means that there's only one thing in the entire universe. Everything in the entire universe is either mass or energy, depending on how you look at it. Yeah. Well, light is energy. It's waves of electromagnetic energy, waves of rippling of the electromagnetic field that we exist in. And the only difference between infrared light and ultraviolet light is the wavelength of those waves. The only difference between X-rays and visible light is wavelength. It's not a different stuff. You know, radiation is not different stuff. It's just electromagnetic energy of some particular wavelength. Well, electromagnetic energy can be described on a spectrum. And the part of the spectrum, that is to say the range of wavelengths that we care about, are centered on the visible light. So visible light is wavelengths of, you know, around 400 nanometers to about 700 nanometers. And a nanometer is a small number, right? Milli, micro, nano. So a nanometer is 1,000th of a millimeter. Milli, micro, nano. Sorry, it's 1,000th of a micrometer, a micron, 1,000th of a micron. So we're talking about wavelengths that are about a half a micron in wavelength, in length. That's visible light, you know, about 400 to about 700. And by no coincidence, that's also the span of wavelengths pretty close to the span of wavelengths that can be absorbed and used to power photosynthesis. It's not a coincidence. I mean, it is, but it's a meaningful coincidence. Obviously, if you remember the names of your colors, red, orange, yellow, green, blue, violet, red is the long wavelengths within that spectrum, you know, up between, you know, 600 and 700 nanometers, and blue and violet are at the other end, down between like 400 and 500. Anything that is too short a wavelength for our eyes to see is called ultraviolet, or if it's just a little too short for us to see. And anything that's a little bit too long for our eyes to see it is called infrared. This is a black and white diagram, and I kind of like a color version of it. And the point is that the visible light is simply part of the whole spectrum. It's the part of the spectrum that the pigments in your eyes absorb. And because they absorb those wavelengths, your brain can sense them. And that's what we call seeing. You can see them. Now, of course, different animals have different pigments in their eyes. So if you were to ask a bird or a bumblebee to define visible light, they would give you, assuming that they could have a meaningful conversation with you about this subject, they would give you different wavelengths. Their definition of the spectrum would be different. The visible spectrum would be different, right? So the reason that we call sort of 380 to 720 light, that's just a consequence of human physiology. These are the wavelengths that our eyes absorb. Wavelength is often indicated with the symbol lambda. That is by far the most common symbol used to indicate wavelength. In terms of frequency, the little f or the Greek letter nu is often used. We're not going to use, I don't think we're ever going to really refer to frequency. We're just going to use wavelength. Wavelength and frequency are completely, totally connected to each other by the speed of light. We'll talk about frequency and wavelength again in about a month from now when we talk about waves of water waves on lakes. But we're not going to talk about frequency with respect to light waves. Now, if you have a beam of light coming, oh, what order do I have my slides in? Oh, if you have a beam of light coming from the sun, and I'm going to shift to drawing on the whiteboard here. That beam of light has three possible fates. Let's say that you've got the sun, and I got three colors of I make sure, I look at Jeffrey to make sure that you can see this. All right, so let's say that we've got the sun here. There's our sun up here, you know, and it's radiating light in all these different directions. And down here, somewhere, you know, we have a lake. Of course, to get to the lake, it's got to go through the atmosphere of the Earth. But if we have a beam of light coming from the sun, it's going to be a mixture of wavelengths of light. Right? I didn't do these in the right order, did I? Oh, yes, it's going to be a mixture. Right? It's going to be white light. It's going to be a mixture of all of these different colors. What are the possible fates of a beam of light? Let's say that we've got, I'm going to do our Earth's atmosphere here. I'm going to make our Earth's atmosphere. We got our atmosphere here. It's not to scale, obviously. What are the three possible fates of a beam of light? Well, one possibility is that it's just going to reflect off the surface. Right? And if it reflects off a cloud or something, it's never going to reach the lake. If it reflects off the surface of the lake, it's not going to get into the water. Another possibility is that it's going to enter the atmosphere, but it's going to get absorbed. You can read that? Can you read that? That's probably not very clear. Write this again. Absorbed. And obviously this happens all the time, right? The light that comes from the sun includes a bunch of ultraviolet wavelengths. And the ultraviolet wavelengths are absorbed by the ozone in the upper atmosphere. And that's how life on the surface of the Earth is possible, right? It's only possible to live up on land because the ozone layer absorbs the ultraviolet. Before there was an ozone layer, the only life on Earth was deep in the water, right? So anyways, one possibility for a beam of light is that it would get absorbed by the substance that it strikes. And the third possibility is that it gets all the way through. And then we say it is transmitted. So there are only three possible fates for a beam of light. It could be reflected, could be absorbed, or maybe that's absorbed, or it could be transmitted all the way through. Now, anything else that you think of is going to be some version or combination of these. If it's reflected, because if the surface has a bunch of, like a rough texture in some way, maybe it's particles, or maybe it's rough, or maybe it's inconsistent and it's heterogeneous. The reflection might not be just like a smooth, perfect reflection. It might be more like scattering. Scattering is really disorganized reflection, or reflection in all kinds of different directions at the same time, not just like one direction like I drew here. But that's what scattering is. Scattering is a version of reflection. And you know that light has the ultimate speed of light, which is the maximum speed of light. But light moves more slowly as it moves through substances. And light has a different speed in different materials. And if the light is doing anything except going into the substance at a perfect right angle, if it's going through the substance at any kind of angle, if the speed of light is different in the two materials, then you'll get a change of direction. And that change of direction is called refraction. You know, something like that, like a change of direction. Without reflection and without being absorbed, it's still 100% there. It's just changed direction a little bit. That's a version of transmitted. And refraction occurs when the light moves from one substance to another one, and its speed is different in the two different materials. So really, there are only three primary fates for a beam of light: reflection, absorption, or transmission. These other things like refraction are variations on that or combinations of them. What is it that determines the fate of a beam of light? It's really determined by only two things. Well, maybe three. Do you know what those two things are? Like, we got a beam of light from the sun. Some of it gets reflected, some of it gets absorbed, and some of it gets transmitted. What determines those fates? What determines which of it is reflected? What determines which of it is absorbed and which part of it is transmitted? So you can put it in the chat if you got an idea. Those of you in plant physiology need to know this, because I mean, I expect you to know because I lectured on it a week, you know, I don't know, 2 or 3 weeks ago. I talked about photosynthesis, right? All right. So the first thing is the properties of the material. And you got a beam of light from the sun. Some of it is absorbed and some of it is transmitted, even though it's striking the same substance, the atmosphere. Why is some of it transmitted and some of it absorbed? Which of it is transmitted and which of it is absorbed? Wavelength. Yeah, right? So the ozone in the upper atmosphere transmits visible light perfectly, but it absorbs ultraviolet. Greenhouse gases in the atmosphere absorb infrared from the Earth, but they let the visible light from the sun right through. So it's the properties of the material, and the wavelength. Now the third thing that's important, I don't know whether you want to consider it a property of the material or a property of objects, but it's kind of the surface geometry. So if there's a third thing, it might be 1B, and that would be surface geometry. And that is to say, if you have water on the surface of the earth, a lake, and the surface is flat, most of the light is going to go right into the water, but a fraction of it will be reflected. It's not a big fraction unless the sun is really, really low and is striking the surface of the water at a very oblique angle. If the sun is very low, so the rays of the sun are not coming in at a steep angle at all, then you can get substantial amount of reflection. The water is the same, the sunlight is the same, but the geometry of the surface is determining whether it is reflected or transmitted. So that's not really a property, a molecular property. I mean, it is, but it isn't. I mean, it is, but it's probably easier to think of that as a separate property, just related to the sort of macroscopic surface geometry. Okay. This is written in the reading notes in the reading questions because Kelf doesn't say it, and I thought you'd want to see it written down, so I wrote it down for you. Okay, going back to my little agenda here. The percent of light that is reflected is the albedo. And I don't have that on a slide, so I'm going to write it on the board. So if you have something like snow or ice or Earth's surface, and you've got sunlight coming down, right? Some of it is going to get absorbed, some of it is going to get reflected. So reflected versus absorbed. Albedo is the percent of the light that's reflected. So some of it's going to be absorbed or transmitted. Some of it's going to be reflected. Albedo is the percent reflected. Boy, you go outside for a walk these days, a bright blue sky, bright sun, white snow. Oh my God, it's just blinding. And that's because snow has a very high albedo. Do you know what the albedo is of freshly fallen snow? Beautiful white snow, the kind that just makes you have to squint your eyes, it's so bright. What percent of sunlight is reflected by freshly fallen snow? You make a guess. And what percent of sunlight is reflected by freshly fallen snow? Put it in the, make a guess, put it in the chat. Yep, 70 to 90%. 0.7 to 0.9. That's the fraction of light that is reflected. So, all right. Let's go back to the slides here for a moment. About this. And you know, water is an interesting substance. H2O in all cases, right? Whether you're talking about snow or ice or liquid water, it's all H2O. But depending on what its form is, it can absorb a lot of light, transmit a lot of light, or even reflect a lot of light. Obviously, freshly fallen snow reflects most of the light that strikes it. But liquid water transmits most of the light that affects it, that strikes it. So the sort of the physical organization of those water molecules can totally change the albedo. Okay. Here's a nice graph just showing you the percent transmittance of water, of light through water, depending on the structure of the water. If the water is like freshly fallen snow, you can see that here we've got 10, this is a log, let's pause and look at a logarithmic axis here. This chart is in CALF, this is figure 10.4. You'll notice that the vertical axis is logarithmic. And what that means is that for every centimeter on the graph, you're multiplying by the same amount. Like in the textbook, this is about an inch. And you can see that as you go up the vertical axis by about 1 inch, you're multiplying by 10. To go another inch, you multiply by 10 again, from 1 to 10. You go up another inch and you go multiply by 10, from 10 to 100. So this is a logarithmic axis, a base 10 logarithmic axis. It's like multiplying by 10 every time you go up an inch. The x-axis, on the other hand, is just a regular linear axis. This distance is about an inch on the page. And as you go from here to here, you're adding 10. You go from 0 to 10. If you go another inch from here to here, you add another 10, 10 to 20. And so this is a linear axis because every time you travel the same distance, you add the same amount. Every time you travel 1 inch, you add 10 centimeters of thickness. This is a logarithmic or an exponential axis, but people call it a logarithmic axis. Every time you travel the same distance, you're multiplying by the same amount. Every time you travel 1 inch on this axis, literally, you're multiplying by 10 in terms of, you know, whatever units it's showing. And it doesn't really matter where you are. Like here, this is 0.1, so this line is 0.2. This is 1, so this is 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you go from this line and you travel 1 inch to this line, you're going from a value of 0.2 to a value of 10 times that, 2. And if you go from here to here, you go from 2 to 20. So it doesn't matter where you are on this axis. If you travel 1 inch, you're going to multiply by 10. That's like the definition of exponential growth. The definition of an exponential axis. You travel the same distance and you multiply by a constant. Okay, to look at graphs with respect to light, you're going to need to think about the fact that it's a logarithmic axis. And you see lots of logarithmic axes in ecology because lots of things have exponential behavior. Populations grow exponentially, so population growth is often drawn with the y-axis logarithmic. So there's lots of times when logarithmic axes are used in ecology because lots of things in ecology are described by exponential functions. Exponential growth, exponential decay, right? Anytime you hear that word exponential, you can guess that the graph is going to have at least one logarithmic axis. Okay, so on this chart, what you're seeing is as the snowpack, for example, is thicker and thicker, the amount of light that goes through decreases. At the very surface, they're saying 10, 20, 30% of the light is transmitted, right? Which corresponds to an albedo of 70%. 70% is reflected, about 30 is transmitted, 10, 20, 30. As the snow gets thicker and thicker, less and less light is allowed through. This is kind of a curve. I would have expected it to be a straight line. I'll explain why. For now, just notice that snow lets the least amount of light through. Like if you had 10 centimeters of snow, you're going to have far less light allowed through than 10 centimeters of ice. When we talk about ice on lakes, there's really two extreme forms that we talk about. One of them is called black ice or clear ice. And the other one is almost universally called white ice. Black ice is not black. Black ice is clear. It just looks black because the water beneath it is dark. And people often call it black ice. In Minnesota, we also talk about black ice on roads, on highways, and when the temperature is below 0, it's fairly common for automobile exhaust, which contains a lot of water vapor, to get condensation and deposition of the vapor as ice. And so when the temperature is below 0 Fahrenheit, you will hear on the news people talking about black ice on the roads. And that's different from when a limnologist talks about black ice on a lake. Black ice on a road is ice typically formed from the conversion of the vapor in automobile exhaust into ice, and you can't even see it. You know, it's more common on bridges than on the solids. Anyways, so Calf pretty much always uses the word black ice to describe this. I would call it clear ice. Clear ice is ice that's just as clear as water. It's ice that formed from lake water freezing. The lake freezes over in November, and then the ice gradually thickens, freezing down, 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 as more and more of the water, more and more of the lake water freezes to the underside of the ice. And that ice tends to have just a beautiful, perfect crystalline structure, great big crystals, very, very clear. And as you can see, virtually no absorbance of the light. I mean, it's hard to even tell if that is not horizontal. It looks like a horizontal line. And that means that once you've gotten past the surface, and the albedo shown in this diagram, 10, 20, 30, 40, 50, 60, this is looking like about 65% of the light entering, which means an albedo of about 35%. But after that, once the light has entered the ice, the light is basically not decreasing at all. It's just shooting straight through the ice. White ice is kind of somewhere in between these two. White ice happens when snow falls on the ice, floods with water, and freezes. If you take snow and you flood it with water, you don't get beautiful, gigantic crystalline structure. You get all kinds of choppy, tiny little specks of ice kind of stuck together by other ice. And it's not clear, it's white, it's opaque. It's essentially snow mixed with water that froze. It's not like dry snowpack, which is snow mixed with air. It's kind of snow mixed with water that freezes. So it's in between these two in terms of how well it transmits light. Okay, well, that's kind of a long description of this, but I'm hoping that you're thinking about actually visualizing ice. When we go out to the lake on Thursday, we're going to look at ice, because hopefully there's going to be ice there's definitely going to be ice in the lake. It's going to be thick because it's been really cold. So be sure to look at the ice and see, is it clear? Is it white? Does it have layers of clear and layers of white? That's often common. The bottom part of the ice sheet might be clear ice and the top part might be white. So make sure that you look for that when you're out on the ice on Thursday. All right, the other thing I want to show here is that, especially, let's look at this white ice line. It's a straight line. It's a straight line on a logarithmic axis. And that means that the amount of light is decreasing exponentially. So at the surface for this white ice line, 10, 20, 30, 40, 50, 50% of the sunlight is entering the lake. At a depth of, I'm going to annotate here, and I'm going to use the square symbol because it's going to help me draw a right angle. At a depth of 10 centimeters, how much light is there? Let's see, 10 centimeters, hit right there, okay. All right, can you look at this chart and tell me how much of the surface light reaches a depth of 10 centimeters in the lake? So I want everybody to give a try at reading the exponential axis here and see if you can tell me how much light does this point right here represent? So right here, if you can see that, this point right here, how much light does that represent? So follow this line over to the x-axis. What is this value here? See if you can read that, and then you can put it in the chat. All right, yes. So just a little bit under 30%, 10, 20, 30. All right, so that is at a thickness of 20 centimeters. If the amount of light in this lake is decreasing exponentially, or the amount in this ice, actually, within the ice is decreasing exponentially, how much light will there be reaching 20 centimeters? Yeah, so here we went from 20, 30, 40, 50. We went from a little over 50 to about 30. How much will there be if we go another 10 centimeters? Well, let's find out. So if you're just doing this roughly, you would say, well, let's say that 10 centimeters eliminated about half of the light. You went from about 50 to about 30. Okay, that's 60%. How much light will go through the next? Well, you would expect that if 10 centimeters absorbs 60% of the light that enters it, then another 10 centimeters is going to absorb 60% of the light that strikes it. So here we have about 20% entering the second 10 centimeters of thickness, using my little right angle here. We would expect 60% of this light to make it to here. 60% of the light that got to this point to make it to here. 60% of 30 is like 18%. Oh, you did the calculation, there we go. And so does this make about 18? Well, we'll follow this over. Follow this line over, and we are about there on the graph. This is between 10 and 20. If you eyeballed it, you'd say it's closer to the 10, but on the other hand, it's not a linear axis. So I would say that this corresponds pretty well. I think 16 is probably a good guess for what this value actually is. All right, so the point is that within lakes, the amount of light decreases exponentially with depth. What this means is if the top meter of water absorbs half the light, then we expect at 1 meter depth, we'll have 50% of the light remaining. If we go down another meter, 50% of that light will be absorbed, and so we expect 25% of the light to reach a depth of 2 meters. So let's look at that on the whiteboard here. I'm going to stop sharing. And then I'm going to all right, as light goes down through a lake, here's a lake. Here we got some light striking it. Let's say that the lake is 3 meters deep. Here's 1 meter, here's 2 meters, here's 3 meters. Of course, limnology, you know, we always put the x-axis at the top. Depth is the vertical axis. I'm going to use z for depth because, you know, x, y, z, you know, if left and right, but anyway, so z is often used for depth. Here we got 1 meter depth. Here we got 2 meters depth. Let's say that in this lake, the amount of light, and light is often indicated with a capital letter I, which I believe stands for insolation, like incoming sunlight, insolation, not insolation, but insolation, incoming sunlight, or incident light. And we pretty much always do this on a scale of 0 to 100%. You know, we can come up with an approximate, we can come up with a measurement of the amount of light striking the surface of the earth. Sorry, the surface of a lake. But a cloud goes across the sun and it changes. A bird flies between you, that changes. You know, a little bit of difference in the texture of the atmosphere, and it changes. So you could put a specific number on that, but you'd be constantly changing the number. So it's pretty typical to just talk about 0 to 100%. So let's say this is 100% of the light that strikes the surface of the lake, and that's 0. If the first meter of water absorbs 50%, then at this depth, 50% of the sunlight will reach it. What percent of the light will reach 2 meters? 25%. How much of the surface light, right? This is what I just explained, right? How much of the light will reach the bottom of the lake? Put it in the chat. Yep. Sol's got the answer. The answer is 12.5%. right? Half, a quarter, an eighth. Now, if we put this on a logarithmic axis, instead of it being even, right, it would be like, how would I do this? It never goes all the way to 0, but let's say that we mark out 4 boundaries. This would be 100%, that would be 10%, that would be 1%, right? If we made this a logarithmic axis, then the numbers would look like this. And you would get a straight line. I tried to draw that as a straight line. It's a straight line. So if you make this axis logarithmic, this exponential decay curve becomes a straight line. What's the formula that describes the amount of light? The amount of light at any depth is equal to the amount of light that strikes the surface times the net multiplication rate, whatever that is. In this case, it's a net division rate, times the depth, or sorry, to the power of z, the number of meters. So if lambda is the fraction of light cut out by the fraction of light allowed through by 1 meter, and then you raise it to the power of how many meters. So lambda equals percent light transmitted per meter. And that's a percent. And z is the number of meters, the depth in meters. It's more typical to represent this with the other version of the exponential function. I sub z equals the initial amount of light times e to the kz. Now, k has to be either a negative number or there has to be a negative sign. It's pretty typical for people to make k a positive number and include a negative sign in their formula. K is called the extinction coefficient. And obviously, e to the negative k is equal to lambda. Right? Because that's what makes these two formulas equivalent, is e to the negative k is just substituted in for lambda. So e to the negative k is equal to lambda. So that means that negative k is equal to the natural logarithm of lambda. All right, now you've used the exponential function before. So let me give you a small problem. Ready for this? Looking at the clock, do we have time for this problem? No, we don't have time for this problem. But the problem I would give you would be something like, you know, if a lake has an extinction coefficient of such and such, how much light will there be at whatever depth? Let me go back to sharing the screen and I'll show you what I mean. Got so excited about the properties of water. Yeah, okay. So here we have a bunch of real lakes. This is a figure from your book. And you will notice that when the x-axis is logarithmic, so here we've got light on the x-axis, and depth is a normal linear axis in the lake. We got a bunch of different lakes here. Here's Crater Lake in Oregon. It's extremely clear water. What you can see is, however, that it declines exponentially with depth, but at a depth of 10 meters, there is still more than 50% of the light available. You look at a lake like Lake Chisholm or Toombs, which are not the slightest bit clear. They're very eutrophic lakes, very murky water. And you could see that even at a depth of 2 meters, there's like less than 1% of surface light remaining. So read those carefully. And in the text, Professor Kalf gives you the extinction coefficients for these lakes so that you can compare how it looks on a graph compared to like how it would look in a formula. Okay, the last thing we want to talk about is the color of light. And in this graph, in this chart here from the textbook, what this is showing you is not only how much light there is as you go down deeper into the lake, but also how the color of light changes. Here's Perry, Toombs, and Chisholm. Here's Perry, Toombs, and Chisholm. So here's the same 3 lakes. On this chart, here is KD, that's K that I wrote on the board, the extinction coefficient. You can see that in Lake Chisholm, the extinction coefficient is like 5. In Perry, the extinction is like 0.2. So in Chisholm, the coefficient extinction is near 5. It's a much bigger number than for Perry. For Perry, the extinction coefficient is a small number. A smaller fraction of the light is eliminated. Am I saying this right? By each. Okay, well, anyways, I'm probably mixing my positives and negatives up as I say that. Sorry. But it's right here, so you can read this clearly without verbal typographical errors. What you also have here is the ZSD, the Secchi disk depth. As you will learn if you've read the lab handout for this week, a rule of thumb for the Secchi disk depth is, it's the depth at which 10% of the surface light reaches. The Secchi disk depth is the depth that 10% of surface light reaches. The deeper the Secchi disk depth, the more clear the water. Now, Professor Kalf almost practically assumes that you already know that, and then he goes into all these details about, some lakes it's more than 10%, and some lakes it's less than 10%, and I wish people wouldn't just use this 10% rule. It's not like, but it's a pretty good rule of thumb, and that's the one we're going to use this week because it's our first time using the Secchi disk depth as a measure, so we're going to start simple. We're going to start simple and just assume the Secchi disk depth is the depth to which 10% of the surface light reaches. I guess the other thing I want to say is that, technically, there's always some light left, no matter how deep you go. I mean, the amount of light is decreasing exponentially, but it's never 0. It's less and less and less and less and less, but it's never 0. So how little light is there when it's too dark? How much light does it take for algae to do enough photosynthesis that they can support themselves? Well, a general rule is 1%. Generally speaking, if there's about 1% of the surface light, that's enough light for algae to do enough photosynthesis to support themselves. That depth is called the compensation depth. And this is, I think, stated in the lab handout for this week. And we're going to use these two things, the Secchius depth and the compensation depth. So looking at these graphs here, one of the things you'll notice is that each graph is a different lake. And these are the 3 lakes shown here. Each of these graphs also gives you an extinction coefficient and a Secchius depth. And then it also gives you a color indicator, which is C, which we're not going to talk about too much. Each of these has the same x-axis, 400 to 750 or so, which is visible light and also basically photosynthetically available radiation, PAR, the wavelengths that photosynthesis can use. Each of these curves shows you the distribution of wavelengths at the different depths. So when you're at a 1 meter depth, indicated here, a 10 centimeter depth, 0.1 meters, this is the distribution of wavelengths. And as you go down deeper into the lake, sort of the peak wavelength doesn't change that much, but the height of the peak changes. On this line here, it's telling you whether you should take this line literally as it is shown, or whether you should mentally multiply it. As you go down deeper into the lake, the amount of light decreases exponentially. And if you put all of these lines on the same vertical axis, you actually wouldn't be able to see these ones. So this line here has been exaggerated by a factor of 3. This line here has been exaggerated by a factor of 9. And this line has been exaggerated by a factor of 48. But they exaggerated them in order to show the spectral distribution, the colors that are available at the different depths. So this is real data from 3 real lakes, and these are all in Tasmania, in Australia. And so they don't follow like a perfect theoretical thing, exactly as you would expect. Now, perfectly clean, clear water, pretty close to Lake Chisholm, or even more so, absorbs blue wavelengths the least, and red and infrared the most. And what you see here is not much change, I think, in the peak. You look at Lake Perry, on the other hand, and you see this big change in color as you go deeper in the water. So there's kind of 2 things here. First of all, these are real lakes with real data, and a kind of graph that we haven't seen before, where individual lines have been multiplied so you can see them. And that's what these little indicators mean. So I would like you to be able to read a graph like this. The general rules that you want to draw from this, these don't really match the theoretical thing, the theoretical simple story very well. Water absorbs red and infrared the best. So if you go down deep in the water, blue light dominates. Blue light is also scattered or reflected by water molecules, primarily, I think, at the edges of bubbles or solutes. So when you look down into the water, what you see reflected at you is mostly blue light. That's why water looks blue. You throw any kind of organic matter dissolved into the water, start talking about realistic real water, and the blue gets absorbed by the organic matter. And as you go down even into this pretty clear lake, and you'll notice that the blue light decreases rapidly with depth. And that's not because of the water, but it's because of the organic matter dissolved in the water. And in all of these cases, you can see the blue light getting absorbed the most, so that as you go down deep, blue is the stuff that's least left. And that's not because of the water per se, but that's because of the stuff dissolved in the water. Water itself transmits blue and absorbs infrared and red. Throw some organic matter in there and you're going to absorb the colors on the other side. They absorb those, the water absorbs those, and you start getting realistic water and it looks green. Throw some algae in and it's going to reflect green and make the water very green too. Okay, I think that's my last slide. I'm afraid I had a lot to say, but very little written on that. But Professor Kalf explains this, and the reading questions direct you to extract it from the reading. And when I skimmed it this morning, I thought, oh yeah, you can see that. All right, do you have any questions? Here we go. Any questions about light in lakes? All right, well, that's what I have for you today. I believe that it is a minute or two after 4, and I have to let you go and get on with your lives, and I got to go over to Menards and buy some stuff for plant physiology lab. Pretty excited. And I will see you all on Thursday, 1 o'clock with bells on. Okay, that's just an expression. Be prepared for lab to take a full 3 hours this week. Nice to see you all. See you on Thursday.